All right, this video is on AP Physics C 2024 actual exam E&M set 1 question 1. Let's talk about this one. A non-conducting rod of uniform positive linear charge density is near a sphere with charge of -2 nanocoulombs. The rod and the sphere are held at rest on the x-axis, shown as figure 1. Equipotential lines in position are labeled. Adjacent tick marks on the x and y-axis are 0.4 meters apart. Calculate the absolute value of the electric flux through the Gaussian surface, whose cross-section is a -20 volt potential equipotential line. So -20 volt equipotential line is clearly this one, and we are supposed to find the electric flux through it, and we know that the formula for the electric flux is given by, as per the Gauss's law, is given by Q inside over epsilon naught. What is Q inside? By the way, they are only interested in the absolute value. So although the Q inside is sphere, sphere's charge is -2 nanocoulombs, but I'm just gonna take it as 2. So that's going to be 2 times, and nano is 10 raised to -9. And what is epsilon naught? Epsilon naught is 8.85 times 10 raised to -12. 8.85 times 10 raised to -12. So let me grab my calculator here. So I'm getting 225, 225,000. I'm sorry, 225.989 Newton. This is flux, right? So that will be either flux is Q inside over epsilon, so that will be Newton meter square per coulomb. That's going to be the unit of it. So this is our answer to the first question. Okay. Let's move on to the next one. Now, a positive charge not shown is placed and held at rest at position C. An external force is applied to the test charge to move the test charge to different positions in order of CEDA. The test charge is momentarily held at rest at each position. So I think I'm going to need this figure once again. Let me borrow this from here. Okay, I'm going to shrink it down a little bit. Okay, I think that will work. The bar shown in figure 2 represents the absolute value of the work done, WCE, by the external force on the test charge to move from C to E. Complete the following tasks on figure 2. Draw a bar to represent the relative absolute work of the work from E to D, likewise work from D to A. And if the work of E to D or D to A is 0, just write 0 in the corresponding column. So we need to find the work from E to D. Where is E? E is here. Where is D? D is here. But guys, don't you think that the work from E to D is just going to be 0, because E and D are on equipotential surface? Not because this is 0. It doesn't really matter whether this is 0 or not. All what matters is there is no change, because they are on equipotential surface, and we know that the work done magnitude is given by Q times delta V. Since there is no delta V, or the change in the potential, the work done from E to D is just 0. Likewise, from D to A, D is here and A is here. The work done, again, they are interested in the magnitude. So the work done is going to be Q times delta V. So it will be Q times delta V is the final potential, which is at A, which is 30, I think. Minus the initial, which is at D, which is 0. So that is 30Q. But they are not really interested in this number. They are interested to so that we can draw the bar of it. And the bar should be relative to this one. So we need to find that what is the work done from C to E as well. Then only we can draw the relative graph, right? Work done from C to E. Where is C? C is here, E is here. So C is at -20 volt and E is at 0 volt. So once again, the absolute value change is going to be 20 minus 0, which is 20Q. So what is the relationship now between 20Q and 30Q? Obviously, this is 1.5 times, right? 1.5 times. So the bars of the first one, the number of bar it is covering is 1, 2, or the number of blocks it is covering is 1, 2, 3, 4, and 4 multiplied with 1.5 is 6. So it means that when we draw the bar of this one, that's going to cover 1, 2, 3, 4, 5, 6, all the way to the top. So this is how I'm going to draw the bar for the absolute value, relative absolute value work of dA. Does this make sense? The next one talks about calculate the approximate magnitude of the x component of the electric field at position B. Where is position B? Again, I'm going to borrow this image. Position B is over here, and uh, we need to find the relative. Sorry, just one second. Yeah, we need to find the x component of the electric field at B. So x component of the electric field can be found using change of potential over change of position, right? Delta V over delta X. I'm not putting negative, actually it is negative, but they are again looking for the magnitude, so I'm not really bothered about the negative. I'll just put absolute value here is this one. Now, what is the change in potential? Obviously, this over here is 10 volts, and let's take another point over here because the electric field is constant, so it doesn't really matter which other point do I take. And this is also an approximation. I know that each of the adjacent points are separated by 0.4. So let's say if I take this one as the other point. So what is the change from negative 20 to 10? That's going to be obviously 10 minus 20, which is 30, right? And what is the x or the distance? I think the distance, if we approximately take this as, at the mark, so this is going to be 0.4, and this is going to be about half of 0.4. I think that is 0.4, right? Just want to make sure. Yeah, that is 0.4. So 0.4 plus 0.2 is, I believe, 0.6. So this is going to be 0.6. So it should be 30 over 0.6. That is the approximate value which I'm getting over here. So yeah, 30 over 0.6 is coming as 50. An electric field unit is volt per meter. Obviously, there is another unit of uh, Newton per coulomb, but volt per meter is also a unit. Both are acceptable. So this is the approximate magnitude of the electric field in the x direction at point B. The next one says that the positive test charge is placed at position D. Now the test charge is then released from rest. Indicate the direction, not the compo. Okay, again, it will make more sense if I can just borrow this. Okay, so they are saying that there's a test charge which is being placed at this position D, and it is released from rest. Now indicate the direction of the net electric field exerted on the test charge immediately after the test charge is released from rest out of these options. And without using equations, justify your answer using physics principles. Okay, first off, we know that I think we are going to justify first and then we are going to find the answer. The first justification is we know that the electric field line is always perpendicular to the equipotential surface. We know that. That's a fact, right? So we know that E is perpendicular to equipotential surface lines. That's the first thing. Now, the only question is whether it is going up or whether it is going down. So we know that the answer is either plus y or minus y, and either directed away from the sphere or towards the sphere. But I know that this is now going to be, this is negative, by the way. This is negative, and the test charge is positive. So what is the force of attraction between negative and positive? That's attractive, correct? So obviously it makes sense that it will go in the plus y direction. So we are just going to say that since this is going to be, since the sphere is negative and test charge is positive, this would mean that the force is attractive in nature, and hence we can say that it is directed towards the sphere, towards the sphere. Of course, we can also argue that there is a rod here, and the rod is positively charged, so it is going to be it is going to repel this. It is going to repel this. But once again, this force, even if we do not take into consideration, this is the one which is leading because this is closer to it. That's one way to understand. Another way to understand is also that electric field lines always go from um, along the electric field lines, potential decreases. So since the potential is getting decreased here, because this is -10, this is -20, so it will make more sense that electric field has to go towards the lower potential. Another reason, if some of you have mentioned this reason, that electric field lines always, um, always go from higher to lower potential. That is also correct because this is a higher potential and now it will be perpendicular always to the equipotential surface, something like, something like this, and it will then terminate on the sphere. So it is always going from higher to lower potential. So we answered both the things. Immediately when it is released, it is towards the plus y and it is directed towards the sphere. That is the answer to this question. Now they are suggesting that the sphere and test charges are removed in the rod of length 4L and a uniform positive linear charge density lambda. The rod is held at rest on the x-axis and the position P not shown is located on the x-axis at distance xp from the origin, where xp is greater than 4L. Electric potential at that point is given by this, so we need to derive this expression. Okay. Let's do that. Let's say xp is somewhere over here. We do not know where it is. Let's say it is somewhere over here. So what we are going to do is we are going to take an elemental mass of this rod. Let's call this dm. And from this dm, we are going to take the distance of that point, right? So we know that this distance is what we are looking for. Now, this is already taken at a distance of x, which is changing. It's a variable, and this complete thing is so-called distance r, on which we need to find the potential. Okay, all right. So what is the potential due to this elemental mass? The potential dV is going to be q or dq. I'm sorry, there's no involvement of mass here. I mistakenly wrote mass, although it will have mass, but we don't need mass. We need charge. So it's dq. So we know that it is k dq over r. That is the potential, correct? Okay. But obviously, I cannot really integrate dq with r because r is a variable, dq is also a variable. So I need to now replace dq in terms of r or x or something like that. Okay, so I know that this is elemental dx and the linear charge density is given by lambda. So the dq charge is going to be the linear charge density multiplied with the length of it, which is dx. So I'm going to now replace dq with lambda times dx, and r is still r, right? We do not know what r is. We have to although convert r in terms of x, which we can do, I think, because this can now be written as k lambda, which is constant. This is dx. And what is r? Don't you think r is this entire thing, which is xp minus this x? So that will give us the remaining length. So I'm going to replace r with xp minus x. And at this point, I'm just going to integrate this. I think a minus sign is going to come out. So I'm going to take that minus outside. So it will become minus k lambda dx over x minus xp. And now I'm going to integrate on both the sides. This is nothing but the change from some 0 to v. That's what we need. And this position, this x is going from 0 to 4L because that's where we are stopping, right? That's where the total charge is concentrated to. So this is going from 0 to 4L. Okay. What will be the integration of this? Dx over x, the integration is going to be natural log. So the left side is just v and the right side is minus k lambda natural log of x minus xp, and the bounds are from 0, absolute value, sorry, there's an absolute value over here as well, from 0 to 4l. So minus k lambda, upper bound minus lower bounds. The upper bound is going to be 4l, so absolute value of 4l minus xp, minus absolute value, minus natural log of absolute value of 0 minus xp, which is just xp. Okay, I'm going to need some more space here, so let me clear this up. Or if you want to see this, I'll just add another slide. So this is going to be what? Let's do away with the absolute value signs, because I know that xp minus 4l minus xp uh, maybe doesn't make much sense, because xp is always greater than 4l. That's given in the question. So I will rewrite this as xp minus 4l and then remove the absolute value sign, because now xp minus 4l is for sure greater than 0. So that's what we need. Minus natural log of absolute value of minus xp can just be written as xp. And what is a log of, in fact, this negative sign can be rammed inside, so it will become k lambda natural log of xp minus natural log of xp minus 4l, and natural log of a minus b is natural log of a, natural log of a minus natural log of b is natural log of a over b. And this is the potential at P. And don't you think this is exactly what we were supposed to prove? I'll go back and you can see that this is the exact expression we were supposed to derive. That's how we do this question. Let's move on to the last one. On this figure 4, sketch a graph of the x component of the electric field from the rod as a function of time. We know that the potential is already this, right? And we need to find the electric field. Let me just borrow this expression over on this page. Okay. Now, what is the electric field? Electric field is given by negative of dV over dx. So I already have the value of potential. I'm just going to find the derivative of this. So that's just going to be negative of k lambda, and then we are going to differentiate natural log of xp. By the way, this xp will now be treated as an x, because after all, xp is nothing but a variable, right? For a general point x, it will just be treated as x over x minus 4l derivative. Okay, I'm again going to write log a minus log a over log of a over b is log a minus log b. It will make more sense, and it will be a little bit easier to differentiate rather than using the chain rule. Derivative of natural log of x is 1 over x. That's derivative of natural log of x minus 4l, ln x minus 4l is 1 over l, 1 over x minus 4l, and this minus goes inside, so it will become k lambda 1 over x minus 4l minus 1 over x. And I think this function looks more like hyperbola kind of. But if you're confused about how this looks like, you can always use a graphical calculator. I can show you how. So over here, what I did is I graphed a similar looking function like this, which is 1 over x minus 1 minus 1 over x. So all I did is replace this k lambda with just 1 and replace this 4l with a number of 1 as well. And you can see that first off, I only need the positive in the positive values of x. So this entirely thing, this can be ignored entirely. And this x minus 1, and since we are interested in greater than 4l as they have mentioned over here, so I need over here greater than x equal to 1, right? Or yeah, x greater than 1. So I drew a line as well, which is x equal to 1, which is over here. And now you can see the only portion which we are interested in is this. And it makes absolute sense that x equal to 1 is a vertical asymptote. So it will go like this fashion, rectangular hyperbola kind of. So here as well, we are going to have a similar curve at x equal to 1. We are x equal to 4l, sorry. We are going to have a vertical asymptote. So the vertical asymptote is going to be like this. and then it will just keep on going and getting smaller and smaller. Don't make it 0 because it won't really be 0 at that point. At 2L, at 12L, because you can clearly see that at 12L this will become 8L and this will become 12L. So it is not 0, it will be some positive number which we do not know, but we know that the shape is pretty much going to look like this, and we can just stop at this point. That's the rough sketch which they wanted from us. So yeah, this is the answer to this question. I hope this makes sense. Any questions, please post it on in the comment section. I'll see you in the next video. Bye-bye.